paper we will discuss today is the overview of the SPARC tokamak. Chapter 2 SPARC and the high-field path to commercial fusion energy. Since the early days of fusion research, the science and technology of tokamaks have made enormous progress. New records were set in the triple product, the primary metric of plasma performance, every few years. Building on this progress, TFTR and JET made another leap forward, setting records not just in triple product, but in DT fusion gain. Unfortunately, however, this progress has largely stalled since the 1990s, while the science of plasma physics and fusion has advanced considerably since that time. The record fusion gains from TFTR and JET still stand many years later. In order to understand what led to this delay in progress, one must ask what the primary factors in increasing the triple product or the fusion gain are as is laid out in the ether physics basics. The progress in the ether physics basis and elsewhere, one can primarily improve fusion performance in three ways. The first is to discover new operating regimes or ways of overcoming non-physical limits. The second is to increase the magnetic field of the machine. The third is to increase the physical size of the machine. In the absence of the discovery of new physics, increased machine performance must rely on either increased magnetic field or increased size. Plotting the achievable fusion gain Q against toroidal field on axis B and measure radius R gives the relationship shown in Figure 1. The calculation in Figure 1 keep epsilon shaping, Q impurity content, and H constant, and limit operation to below 0.9 n. Note that this particular calculation considers only core confinement and does not take into account plasma exhaust, neutron loading, or engineering constraints. The gain is a non-linear function of both field and size, and by increasing field, one can decrease size and obtain the same gain without changing any physics assumptions. The good agreement between the Q contours in Figure 1 and predictions or observations from other machine design points reveal the generality of the relationship between toroidal field size and gain. This motivates aiming for the highest field possible given technological constraints. On the path to commercial fusion energy, one must also consider the applicability of any given technology to an economical power plant. For this reason, it is infeasible to use copper toroidal field magnet, as it would be extremely challenging for a power plant to overcome the electricity cost of running the magnets. This has led to the general conclusion that any viable power plant must have superconducting magnets. At the time of ITER's design, the state-of-the-art superconductor was NV3SN, and the magnetic field that practically achievable with available superconducting materials limited to approximately 13 Tesla on the conductor. This field on coil in a standard aspect ratio tokamak, epsilon equals 0.3, limited to the field on axis to roughly 5 or 6 Tesla. As Figure 1 shows, limiting the toroidal field to 5.3 Tesla requires a measure radius of approximately 6 meters to achieve Q equal 10. In this sense, ITER FEAT was designed to be the smallest machine that would achieve Q equal 10 while respecting hard limits in the allowable magnetic field given the technology at the time. Unfortunately, anything this large is inevitably expensive and time-consuming, which along with other political and organizational factors arising from the scale of the undertaking contributed to the slowed progress in fusion gain over the last 20 years. The pace and cost of such large complex projects also do not bode well for the economic viability of a commercial power plant. Based on this approach, the current EU demo design point is also shown in Figure 1. Note that the shaping for EU demo is less than is assuming in Figure 1, and so the projected performance of Euro demo Q equal 14 is less than that indicated. Even at the time of ITER's design, however, it was recognized that without the constraint in magnetic field, it would be possible to build a high-gain device that was much smaller. This sentiment is manifested in designs for several high-field copper devices, such as CIT, BPX, FIRE, and igniter, that aim to achieve high gain on much smaller scales than ITER. These devices followed the high-field path of the Alcator series of tokamaks and aimed at accessing high gain with the knowledge that their magnet technology would not be applicable in a power plant. Given what has been discovered since their design, it still seems likely that these machines would have achieved break-even if they had been constructed. BPX, CIT, FIRE, and igniter are also shown in Figure 1 and fall right along the Q equal 10Q curve. In recent years, however, new HTS materials have emerged as viable alternatives to older low-temperature superconductor ones. One of these, REBCO, has previously been recognized as having the potential for use in fusion magnets, but until recently was not mature enough for large-scale production. Now it is available in large quantities and at high performance and provides access to much higher magnetic fields than was possible with NB3SN. This technology allows for a new design optimization of a superconducting Q bigger than 1 tokamak, with different engineering constraints but built on the same physics basis as ITER. As was the case when ITER was designed, a Q bigger than 1 device is still an essential part of any path to a fusion power plant for political and commercial seasons. SPARC's missions of Q bigger than 2 achieves this milestone with enough margin to be definitive. Achieving a burning plasma Q equal 5 would also unlock access to new physics regimes that have not been explored on current devices. With the existence of HTS magnets, however, one can build a much smaller device, smaller in scale to current devices, such as D3D, ASDEX upgrade, EASD, and K-star, and achieve these goals quickly and at low cost. Perhaps even more importantly, this technology may lead to an economical, attractive power plant, which will be essential for the widespread adoption of fusion energy. SPARC is a result of combining new HTS technology with the same proven physics that lead to the ITER, CIT, BPX, and FIRE designs with R equal 1.85 meter and B equal 20.2 Tesla. SPARC falls onto a smaller Q curve in figure 1 to ITER, achieving Q equal 10 under nominal physics assumptions. So at roughly 2% of the volume of ITER, this operating point provides considerable margin over SPARC's mission of Q bigger than 2 to account for various uncertainties such as the scatter in the confinement scaling relationship, the natural progression from SPARC is then a power plant based on HTS embodied in the arc design. In Figure 1, the arc power plant is considerably smaller and thus will likely be considerably less expensive than larger designs based on LTS, such as Eurodemo, through detailed costing estimates require further engineering design. SPARC is being designed jointly by Commonwealth Fusion Systems and the Massachusetts Institute of Technology Plasma Science and Fusion Center. The SPARC project is well underway and has been divided into two main phases. Phase 1 lasts 3 years and consists of two major milestones. One, the construction and operation of an HTS-based toroidal field model coil, and two, the completion of the SPARC design. Early phase 1 work from testing of high current HTS cables in background magnetic fields has recently demonstrated excellent performance at SPARC-relevant electromagnetic loading and thousands of cycles. The SPARC device design has moved through several iterations to reach its current state. The V design stood from 2018 until mid-2019 and was used to assess the overall viability of the project, including analysis of key subsystems from mid-2019 through early 2020. There were 5 V iterations, including the V-C iteration presented at APS DPP 2019. The primary focus of the V iterations was to further increase the self-consistent engineering validity across systems and to increase the conservative nature of the fusion gain performance. Moving forward, the SPARC version 2 design described in this article stands as the baseline. Phase 2 is projected to last 4 years and consist of completing the last stages of the tokamak design, as well as construction and commissioning of the device. This timeline is intentionally aggressive, approximately 7 years from start of design to start of SPARC operations, 3, but has historical precedent in the design, construction, and commissioning of previous devices, such as TFTR and JET. Plasma operations in SPARC will begin with brief campaigns in helium, hydrogen, and deuterium in order to build experience with operations and refine performance projections. Among other things, SPARC will then move as rapidly as possible to deuterium tritium operation and Q bigger than 2, while the exact duration of helium, hydrogen, and deuterium operation is uncertain. All efforts will be made to optimize the path to full power DT operation by utilizing the experience developed through operation of other tokamaks. Following the operation of SPARC, CFS plans to complete fusion's transition from laboratory to market by moving as rapidly as possible to the construction and operation of a pilot commercial fusion power plant, likely based on the ARC design and the lessons learned on SPARC.